If you took a, um, a perfectly sealed industrial steel drum-like, completely empty except for the air inside, and you just dropped it off the side of a boat, it wouldn't just float down gently to the seafloor,
No, definitely not.
right? Because as it sinks deeper and deeper, the sheer weight of the ocean above it would, begin to press inward.
Yeah, the hydrostatic pressure is immense.
Exactly. And by the time that drum reached, say, 800 meters down into the abyssal zone, the water pressure would just violently crush it flat, like a discarded soda can.
Just instant structural failure.
It's a terrifying, totally unforgiving environment. And for decades, if you look at the history of marine engineering, we've basically treated that crushing abyss as an enemy.
That really is the dominant paradigm.
Right. We build thicker submarine hulls, we cast these massive titanium spheres, and we engineer, complex high-stress seals. The entire philosophy is defensive.
You're spending massive amounts of capital and engineering effort simply to resist the environment.
Just a constant, expensive battle against physics to keep the ocean out. But today, we are taking a deep dive into a stack of source material that asks a completely crazy, completely brilliant question.
It really is a massive shift in perspective.
Yeah, it asks, what if we stop fighting it? For you listening, whether you're prepping for a meeting or trying to catch up on the latest engineering shifts, or you're just someone who loves dodging information overload to find those structural aha moments, this is going to be a wild ride.
It absolutely is.
We are unpacking a dense, brand-new, formal concept paper. This was published in March 2026 by an independent researcher named Zachary David Enfield.
And the blueprint he's laying out, it doesn't just suggest a new type of machine.
No, it's bigger than that.
Right. It suggests an entirely new way of looking at extreme natural forces.
Yeah.
Enfield is proposing that we take that terrifying, crushing hydrostatic pressure at 800 meters, and instead of spending millions of dollars trying to build a wall against it, we invite it in.
Which sounds completely counterintuitive.
It does, but he wants to use it as a foundational design variable, basically as a hypercharged battery.
Okay, so let's unpack this. The concept is called the Step Pressure High Bar Oscillating Water Column, or the SPHBOWC for short.
It is definitely a mouthful of an acronym.
A huge mouthful. But before we sink this imaginary machine into the pitch-black depths, we really need to understand what it actually looks like on the surface.
Yeah, that's crucial because the author didn't invent the core technology from scratch.
Right, he's taking something that already exists, something highly proven, and radically altering its environment.
To understand the leap this paper is making, we first have to ground ourselves in the traditional oscillating water column, or OWC.
And this isn't science fiction, right?
Not at all. It's a technology that's been conceptually understood for decades and physically operating in the real world for years. The paper references several key installations to prove we are starting with mature physics.
Yeah, the sources explicitly point to the Linkit plant on the Isle of Islay in Scotland. And they mention the Mutriku wave power station built right into a breakwater in Spain and the Yeongsu plant off the coast of South Korea.
All excellent real-world examples.
So if you were to walk up to one of these stations today, what are you actually looking at? Like, how do they capture the power of a wave?
Well, if you stand near the Mutriku station, for instance, you are looking at a massive, heavily reinforced concrete structure. It's sitting right on the coastline, taking the full, violent brunt of the incoming ocean wave.
Just getting smashed by the surf.
Exactly. And part of this concrete structure extends down below the waterline. Now, inside this structure is a hollow chamber, and the very bottom of this chamber is open to the sea.
Okay, so the water can just freely slosh in and out of the bottom of the room.
Precisely. But the top of the chamber is sealed tight, trapping a large pocket of air above the water.
Got it.
So when a wave rolls in from the ocean, the crest of that wave forces water up through the bottom opening. The water level inside the concrete chamber rapidly rises.
And as that water rises, it acts exactly like a giant hydraulic piston.
Yes. It physically pushes up against the trapped air, compressing it.
And because the room is sealed, that air has only one possible escape route.
It's forced up through a narrow duct at the very top of the chamber. And housed inside that duct is an air-driven turbine.
So the highly pressurized air screams past the turbine blades, spins a generator, and creates electricity.
Right. And then the wave crashes, the water recedes, and the trough of the wave pulls the water level back down.
Which creates a vacuum inside the chamber.
Exactly. The massive drop in the water level sucks fresh air back into the system from the outside atmosphere, pulling it down through that same duct, past that same turbine.
I've always found the turbine design for these things fascinating, by the way.
Oh, the Wells turbine.
Yeah, the sources mention the Wells turbine. Because if the air is being pushed up and then sucked back down, a normal fan would just spin one way, stop, and then spin the other way. You'd lose all your momentum.
Right, that would be terribly inefficient. But the Wells turbine is an elegant piece of engineering. Its blades are symmetrical and shaped like airplane wings.
So it doesn't matter which way the wind blows.
Exactly. Because of the specific aerodynamic profile, the turbine continues to spin in the exact same direction, regardless of whether the air is rushing outward during a wave crest or rushing inward during a wave trough.
It harvests energy on both the exhale and the inhale.
It does.
It's basically a gigantic set of concrete lungs breathing in and out with the rhythm of the ocean's surface. And the paper makes it clear we know how to build these lungs. The physics of the surface OWC are completely validated.
Yes, we have prototypes reaching technology readiness levels of 8 or 9. The problem isn't the physics at all.
The problem, as always, is the money.
Always the money. The economics of surface wave energy have historically been brutal. The ocean surface is an incredibly chaotic and destructive place.
Yeah, I mean, you have to build a concrete chamber strong enough to withstand a once-in-a-century winter storm.
Right, and your capital expenditures just skyrocket. You are pouring thousands of tons of concrete and steel just to protect the machine from getting ripped apart.
And what are you getting in return for all that concrete? The sources say the average power density of these surface OWCs is something like 15 to 25 kilowatts per meter of device width.
Which is very low.
Yeah, it just doesn't mathematically compete with a modern offshore wind turbine.
It really doesn't. And that harsh economic reality is the springboard for Enfield's entire thesis. You see, a traditional OWC operates at sea level.
Right.
The air inside that concrete chamber, before a wave hits it, is sitting at standard atmospheric pressure 1 bar. The entire pneumatic event is built on soft, low-density surface air.
Which brings us to the paper's radical departure. What if we take this proven concrete lung concept and we don't build it on a rocky cliff in Scotland? What if we sink it 800 meters straight down into the abyssal zone?
This is where we crossed from standard engineering into a completely different thermodynamic environment. Depth is no longer just a location.
Right, it becomes a tool.
Yes, it becomes an active, fundamental design variable. To truly grasp why this matters, we have to look closely at the physics of hydrostatic pressure.
The weight of the water.
Exactly. For every 10 meters you descend into the ocean, the hydrostatic pressure increases by approximately 1 atmosphere. That's roughly 101 kilopascals of force added every 10 meters.
So, if I dive 10 meters down into a pool, my ears feel the pressure of the air above the pool, plus 1 full atmosphere of water pushing against me.
You've got it. And now follow that math down to the conceptual baseline Enfield uses for the SPHBOWC. At 800 meters deep, a device is subjected to an ambient pressure of approximately 80 bar absolute.
Wow, 80 bar.
And if we drop all the way down to 4,000 meters, which the National Oceanic and Atmospheric Administration defines as the upper reaches of the true abyssal zone, the pressure approaches 400 bar.
That is just wild. 80 times the pressure of the atmosphere we are sitting in right now.
It is immense.
But again, as we established up top, we know how to build things that can survive 80 bar. The offshore oil and gas industry runs pipelines and wellheads at those depths all the time.
Right. Survival is a known engineering feat.
Yeah, we can build a steel box that doesn't crumple. But that's just survival. How does that 80 bar environment actually amplify the power of the machine?
The amplification comes from the way gases behave when they are trapped and compressed. The paper leans heavily on polytropic gas behavior.
Okay, polytropic gas behavior.
Specifically, the thermodynamics of rapid compression where the gas doesn't have time to exchange heat with its surroundings.
Let's keep this grounded in physical reality for a second. If I have a chamber full of air and I smash a piston into it really fast, what is actually happening to the molecules inside?
When you compress a gas quickly, you are doing work on it. You are forcing the gas molecules into a much tighter space. Because they are crowded, they collide with each other and with the walls of the chamber much more frequently.
And with much greater energy.
Exactly. And this manifests as a sharp spike in temperature. The gas physically heats up.
And because this happens in a split second, as a wave crashes in, that heat has nowhere to go.
Right.
It can't bleed out into the surrounding steel or concrete fast enough.
That's the key. And because the heat is trapped inside the gas, the pressure spikes even higher than it would if the temperature remained constant. The gas pushes back with tremendous force.
Okay, I'm following.
Now, let's apply this to our two environments. In a traditional surface OWC sitting at 1 bar, a wave rolls in and pushes the water piston up. Let's say that water movement shrinks the available air volume inside the chamber by 5%.
Just a 5% squeeze on soft surface air.
Right. That 5% volume reduction produces a relatively modest absolute pressure swing. You might get a fraction of a single bar of pressure pushing against your turbine. You are extracting energy from a very soft, highly compressible medium.
But if we take that exact same physical chamber with the exact same 5% volume reduction and we do it at 800 meters.
At 800 meters, the baseline pressure of the trapped air sitting inside that chamber is already 80 bar.
Right.
It has been pre-compressed by the weight of the ocean simply by being down there. It is incredibly dense. If a deep ocean force drives water into the chamber and shrinks that highly dense air volume by the exact same 5%, the resulting absolute pressure excursion is roughly 80 times larger.
That is the massive aha moment of the paper.
Huh.
You are starting with air that is already packed with potential energy just by virtue of its depth.
Exactly. The gas spring stiffness scales directly with the baseline absolute pressure. If you have a turbine that is being driven by a 4-bar pressure swing sitting on top of an 80-bar baseline, you are extracting vastly more energy per unit of chamber volume than the identical chamber operating at the surface.
You've fundamentally increased the energy density of every single wave stroke.
Exactly.
I think the best way to visualize this is to think about a standard plastic syringe, the kind a doctor uses, but completely empty except for air.
That's a great analogy.
Yeah, so if you stand in your kitchen, put your thumb tightly over the tip, and push the plunger down 1/4 of an inch, you feel a little bit of resistance, right? The air pushes back against your thumb. That's the soft 1-bar gas spring of our surface, OWC.
That is the baseline state on the surface.
Right. Now keep your thumb tightly over the tip of that syringe, and imagine you are instantly teleported outside a submarine at 800 meters deep.
Which would be quite a shock.
Right. The crushing weight of the ocean all around you has already forced that plunger in, compressing the air inside until it equals the 80-bar pressure outside.
The air inside that little plastic tube is now incredibly thick and dense.
Exactly. Now, if you try to take your finger and push that plunger down another 1/4 of an inch, it is going to fight you with 80 times the force. The spring has become incredibly stiff.
And that syringe analogy leads us directly into the primary engineering hurdle of the entire paper. The paper refers to this as the paired penalty.
The paired penalty.
Yes. The physics give us a massive hyper-dense amplification of power, but they penalize us with that incredibly stiff spring.
Yeah, and this is where I actually hit a wall when I was reading the source material. I literally wrote a big question mark in my notes.
What was the question?
Well, if the gas spring inside that chamber at 800 meters is 80 times stiffer than it is on the surface, doesn't that just mean the incoming wave hits a brick wall?
Yeah.
Because if the water tries to push up into the chamber, but the 80-bar air refuses to compress because it's so dense, the water just bounces off. You can't generate power if the water column freezes in place. The lungs can't breathe.
That is a fundamental hydrodynamic problem, and it proves exactly why you cannot simply unbolt a surface OWC from a cliff in Scotland, drop it to the seafloor, and expect it to work.
It would just break.
Or it just wouldn't move. If you drop a standard limpet plant to 800 meters, the water column will completely lock up. The wave will hit the air pocket won't yield, and the energy will just be reflected back out into the ocean. The entire system has to be fundamentally retuned.
So how does Enfield propose we tune an 80-bar brick wall so that the water can actually move?
By drastically redesigning the compliance of the system. In fluid dynamics, we treat the oscillating water column inside the chamber as a mass spring damper system.
Okay, mass spring damper.
Right. The mass is the physical weight of the moving water. The damper is the energy being extracted by the turbine. And the spring is the trapped gas volume. To manage a spring that is 80 times stiffer, you must introduce, with the paper terms, compliance accessories.
Compliance accessories. Okay, so in practical physical terms, what are we actually building?
We are building secondary air reservoirs. Think of them as sidecars or auxiliary accumulators connected to the main central chamber by carefully engineered pipes and throttle valves.
Oh, so they're like overflow tanks.
Essentially, yes. When the immense hydraulic force of the deep ocean surges upward into the main chamber and that 80-bar gas spring begins to resist too violently, these accumulators can selectively open.
And take the pressure off.
Exactly. They absorb a precisely calculated fraction of that dense gas. By giving the air a place to expand into, you effectively soften the apparent spring constant of the main chamber.
That's brilliant. You are dynamically tricking the water into thinking the room is bigger than it actually is, just long enough for the water to complete its upward stroke.
You adjust the stiffness on the fly so the water piston can fully rise and transfer its kinetic energy, but you keep all that dense air contained within the closed system so you don't lose the pressure required to drive the turbine.
Wow.
It is a highly complex, staged compliance management system. The volume of the chamber, the size of the accumulators, the diameter of the throttle valves, these are no longer simple geometric choices. They are deep ocean thermodynamic variables.
Okay, assuming we can mathematically tune this system to breathe at 80 bar without locking up, we run into an even bigger mystery.
Yeah.
We are sitting at 800 meters down. It is pitch black. It is freezing cold. And most importantly, it is dead calm.
Yes, the deep ocean is generally very still.
Right. Surface waves, the massive frothing, crashing waves that drive surface OWCs, do not reach 800 meters down. The energy of a surface wave decays exponentially the deeper you go. By the time you hit the abyssal zone, a raging hurricane on the surface feels like absolutely nothing.
He wouldn't even know it was happening.
Exactly. So if there are no waves to push our giant water piston into that incredibly stiff gas spring, where is the energy actually coming from?
Which brings us to subsystem 1 of the SPHB-OWC architecture, catching the invisible waves.
Invisible waves.
Yes. A machine built for the abyssal zone must decouple itself entirely from surface weather and couple itself to a completely different hidden forcing regime.
The paper cites oceanic research into thermohaline circulation. What is actually moving down there in the dark?
The deep ocean is far from static. It is a constantly moving, highly structured conveyor belt of water, driven primarily by massive gradients in temperature and salinity.
Okay.
Cold, dense, salty water sinks at the poles and creeps along the abyssal plains, while warmer water moves above it. This creates abyssal currents.
But the sources are clear that abyssal currents are incredibly slow. We're talking about water moving at maybe 2 to 5 centimeters per second. That is a sluggish crawl.
It really is.
And a sluggish crawl doesn't have the violent oscillating punch needed to compress an 80-bar spring.
You are absolutely right. A slow, steady current won't work for an oscillating machine. The true prize in the deep ocean, the vast, untapped energy source this machine is hunting for, are internal waves.
I have to say, I found the description of internal waves to be the most poetic part of the whole paper.
They are a staggering natural phenomenon. Internal waves do not happen at the boundary between the ocean and the air. They happen entirely underwater at the boundary layers between different densities of water.
Because the ocean is stratified.
Exactly, meaning you have lighter, warmer water sitting on top of heavier, colder, saltier water. And those boundary layers can ripple and undulate just like the surface of a pond.
And these internal waves aren't small, right? They can be massive.
They can be hundreds of meters tall, rolling slowly through the deep ocean, carrying immense amounts of kinetic energy. And crucially for our machine, the paper focuses on internal tides.
Internal tides.
Yes, these occur when regular tidal forces pull massive layers of stratified deep water back and forth across jagged seafloor bathymetry.
So, imagine a massive underwater mountain range, like a seamount. As the moon's gravity pulls the tide, a continent-sized slab of dense, cold water is dragged forcibly up and over that underwater mountain range.
Right.
And the friction and the collision with the rock create huge, rhythmic underwater ripples.
Exactly. And unlike a surface storm, which is wildly unpredictable and chaotic, an internal tide is highly periodic. It is driven by the moon and the bathymetry. It is reliable.
Which is exactly what you want for power generation.
Right. And its energy is geographically concentrated around specific topographic features like continental slopes and oceanic ridges.
But the energy is slow. It's a massive, slow-rolling pulse of water, not a sharp, crashing wave.
Yeah.
To capture that slow energy and use it to punch our stiff gas spring, the paper lays out 4 specific intake designs.
Yes.
The author doesn't just offer one blunt pipe. He proposes a whole catalog of deep-sea funnels to shape the water.
The intake geometry is critical because you are trying to translate a slow, massive, horizontal movement of water into a fast, vertical, high-pressure strike. Let's examine the 4 families of intakes the paper proposes.
The first one's called the directional abyssal scoop. The paper describes it as a curved, flared opening that sweeps forward to catch the predominant deep current.
Which makes intuitive sense.
Yeah. If the internal tide reliably flows back and forth along a specific underwater valley, you point this giant scoop directly into the flow. It immediately made me think of the nacelle on a wind turbine, how it automatically swivels to face the breeze so it doesn't miss any kinetic energy.
It's a matter of vector alignment. If you know
Yep.
exactly where the internal wave is coming from because the underwater mountain range forces it down a specific path, you optimize the capture area to face it directly.
The second design is the throated pulse inlet. The paper mentions applying the continuity equation here. I know you know what that is.
Yeah.
But for those of us who aren't fluid dynamicists, how does trading cross-sectional area for inlet velocity actually work?
The principle of continuity states that for an incompressible fluid like water, the mass flow rate must remain constant throughout a pipe.
Okay.
So if you have a massive volume of water moving slowly through a very wide opening, and you suddenly force all that water to squeeze through a much narrower opening, the water has no choice but to dramatically speed up to get through in the same amount of time.
Oh, it's a classic garden hose trick.
Exactly.
Yeah, if water is lazily pouring out of the end of the hose and you stick your thumb over half the opening, the water suddenly sprays out in a fast high-pressure jet.
Precisely. By placing a constricted throat at the intake, the sluggish 5 centimeter per second internal wave is forced through a bottleneck. It accelerates, gaining the kinetic energy and momentum required to actually strike the gas spring inside the chamber with meaningful force.
Okay, that makes sense. The third design is the check-valved surge inlet. This one introduces moving parts. It uses one-way mechanical valves that allow water to violently rush into the chamber, but then instantly snap shut to prevent the water from just flowing back out when the internal wave passes.
It creates asymmetric charging. When the massive internal wave pushes against the machine, you want the chamber doors to swing wide open so you can swallow all that pressurized water.
Swallow it all whole.
Yes. But internal waves are oscillatory. The pressure will eventually drop. When it does, you do not want to lose the hydraulic head you just captured.
Right. Think of it like a turnstile at a busy subway station. During rush hour, a massive crowd of people pushes through the turnstile, and it spins freely, letting everyone into the station.
But the second the crowd stops,
And tries to push backward out the door, the turnstile ratchets and locks solid. The water is trapped inside the station.
that mechanical rectification ensures the stored energy inside the central chamber is maximized before the gas spring begins its upward stroke.
And the fourth intake family is the stepped chambered basin. This is where the machine stops looking like a discrete device and starts blending into the geology.
This is a really elegant design.
It is. The paper suggests using the seabed itself as a design element. Instead of building a blunt metal funnel, you carve or cast a sequential series of step ledges leading up to the machine, like a giant underwater staircase.
This leverages hydrodynamic shoaling and resonance. When an internal wave travels over a flat abyssal plane, its energy is diffuse.
That's spread out.
Right. But as it encounters rising step topography, the wave is compressed vertically, its amplitude grows.
It builds up.
By carefully engineering the shape of the seabed directly in front of the intake, computational fluid dynamics show you can significantly amplify the wave before it ever touches the metal of the machine. The geology becomes the first stage of the intake funnel.
All of these intake designs, the directional scoop, the restricted throat, the turnstile valves, the underwater staircase, they all exist to solve one specific problem, which the paper calls the abyssal pulse piston mode. And this is a crucial point of clarification for anyone trying to visualize this machine.
Yes, there is a very common misconception when visualizing deep water pressure systems.
That's the misconception.
Well, when people hear we have a machine operating under 80 bar of pressure, they naturally assume the goal is to just open a valve at the bottom, let the 80 bar water blast into the pipe, and create a continuous roaring geyser of water shooting all the way up to the surface.
Like an uncapped oil well or an underwater volcano, just venting all that deep pressure directly up a pipe to spin a water wheel.
But Enfield is adamant that this is the worst possible way to extract the energy.
Why is that?
Because squirting 80 bar water directly up an 800-meter pipe exposes the system to immense frictional losses. The static abyssal pressure is a stored condition. It is the environment. If you vent it, you waste it.
So if we aren't creating a giant underwater geyser, what is the machine actually doing with the water?
The machine is designed to capture the dynamic, moving component of the internal wave, run it through those specialized intakes, and form it into a controlled, highly coherent hydraulic slug inside the lower vertical riser of the machine.
A hydraulic slug, like a solid, heavy punch of water.
Exactly. The water doesn't rush to the surface. It surges upward just far enough to act as a massive, unstoppable piston. It slams into the trapped volume of gas, transfers all of its kinetic energy into compressing that 80 bar gas spring, and then its job is done. It recedes, preparing for the next internal wave to hit.
The water is just the hammer. The gas is the nail.
The gas phase is the true isolated power delivery medium of the SPHBOWC.
Okay, we have managed to locate the hidden internal tides rolling over the seamounts. We have used a stepped bathymetric staircase and a throated nozzle to shape that slow, massive energy into a sharp, coherent hydraulic slug. And we've slammed that slug upward into our incredibly dense 80-bar gas spring.
The energy's now in the air.
Right. But now what exactly does that highly pressurized, repeating blast of air hit? Because we haven't even talked about generating electricity yet. This brings us to the belly of the beast, subsystems 2 and 3, the central chamber and the buffer loops.
Subsystem 2 is the high-bar trapped gas chamber. This is the central heart of the architecture. It is the physical space where the wet, heavy, chaotic energy of the ocean transfers into the dry, compressible energy of the pneumatic circuit.
And the engineering requirements for this room are brutal. The paper lays out 3 competing priorities. First, the room has to be large enough to hold a massive volume of air, otherwise that 80-bar spring becomes too stiff and the water piston just bounces off.
Right.
Second, it needs all those compliance accessories, the overflow tanks and throttle valves, plumbed directly into it. But the third requirement is the real nightmare, structural rigidity.
The rigidity of this central chamber dictates the survival of the entire thermodynamic cycle. If you calculate that you need exactly 500 cubic meters of air volume to achieve the perfect spring stiffness, the walls of that chamber cannot flex.
At all.
Not at all. If an internal wave hits, the pressure spikes to 90 bar, and the steel walls bulge outward by even a few centimeters, your volume has changed.
And if the volume changes, the spring constant changes.
Precisely. If the walls expand under pressure, the spring gets softer, the stroke length changes, the timing is ruined, and the entire mass spring damper system detunes itself. The walls must be almost infinitely rigid against massive, repeating differential pressure spikes.
Let's assume we build a perfectly rigid titanium-reinforced bunker that doesn't flex a millimeter. We now have a chamber breathing in and out, creating these massive, violent spikes of dense 80-bar pneumatic power.
It's an intense environment inside there.
But here is where anyone who knows anything about electricity generation will spot a major problem. And the paper addresses it heavily in Subsystem 3. Ocean waves, whether they are crashing on a beach in Scotland or rolling slowly over an abyssal plain at 800 meters, are inherently messy.
Very messy.
They are bidirectional burps of energy. The water surges up, it pauses, and it sucks back down. The air pushes violently up, it pauses, and it sucks violently back down. And then what I understand, delicate, high-speed turbo machinery absolutely hates messy, bidirectional, pulsing airflow.
Oh, they despise it. Turbines are precision instruments. They achieve their highest aerodynamic efficiencies when they are fed a perfectly smooth, unidirectional, continuous flow of fluid at their specific design speed.
So if you pipe a wave into it,
If you take the raw, chaotic, back-and-forth screaming of a wave chamber and pop it directly into a standard turbine, the turbine suffers immensely. It accelerates, stalls, reverses, and accelerates again. The cycle averaged power output plummets, and the mechanical fatigue on the bearings is catastrophic.
the traditional surface OWCs try to solve this with the Wells turbine, letting it spin the same way while the air goes back and forth. But Enfield says that's not good enough for an 80-bar system.
It's just too violent at that pressure.
So he introduces Subsystem 3, the closed-circuit pneumatic buffer loop. How does this system tame the chaos?
It is a brilliantly simple fluid routing solution that completely insulates the turbine from the chaos of the ocean. Instead of connecting the main breathe-in chamber directly to the turbine, Enfield interposes 2 massive staged buffer volumes.
Okay, 2 buffers.
Right. You place a high-pressure buffer tank upstream of the turbine and a low-pressure buffer tank downstream of the turbine.
And you separate everything with heavy-duty check valves.
Yes. Think of the check valves as one-way doors for the air. When the internal tide surges upward and compresses the gas spring to its maximum pressure, that intensely packed air bursts through a one-way valve and fills the high-pressure buffer tank. Once the tank is pressurized, the valve snaps shut.
The air cannot return to the main chamber.
It cannot return.
It basically stockpiles the pneumatic energy. It hoards all that high-pressure air in a holding pen.
Exactly. And on the far side of the turbine is the low-pressure buffer tank. Its job is to collect the expanded, used air after it has passed through the turbine blades, holding it until the main chamber enters its suction stroke and pulls that exhaust air back in to be reused.
The turbine sits perfectly protected between these two massive holding pens.
Because the high-pressure buffer is constantly being topped up by the erratic wave strokes, it maintains a relatively steady, constant high pressure. And because the low-pressure buffer is constantly being evacuated, it maintains a steady low pressure.
So the turbine just sees a calm breeze.
Exactly. From the perspective of the turbine sitting between them, there are no chaotic waves. There is no back and forth surging. The turbine simply experiences a smooth, sustained, unidirectional breeze flowing from the high-pressure tank to the low-pressure tank.
It essentially acts as a pneumatic capacitor. It absorbs the alternating current of the chaotic ocean and outputs a smooth, steady, direct current of air for the turbine.
That's a great way to put it.
Now, the paper is quick to point out that this smoothing architecture isn't totally unprecedented. We aren't inventing the concept of buffer tanks from scratch.
No, the architecture draws heavily on adjacent, highly active research fields. The paper cites the Tupperwave OWC project, which is currently validating similar rectifier configurations for wave energy. But the more profound parallel is with underwater compressed air energy storage, or UWCAES.
UWCAES, storing energy underwater.
Yes. UWCAES research has definitively proven the value of isobaric subsea storage. If you store compressed air in a rigid tank at the bottom of the ocean, the immense surrounding hydrostatic pressure helps maintain the density of the stored gas.
Oh, that makes total sense.
Enfield is leveraging this exact principle. By placing the buffer tanks at depth, the extreme environment actually stabilizes the high-pressure stockpile, ensuring the turbine operates constantly at its most efficient aerodynamic design point.
Okay, let's pause and take stock of what we've built in our minds so far.
It's quite the machine.
It really is. We are sitting in the freezing dark, 800 meters below the surface. We have a stepped bathymetric staircase carved into the seafloor that catches an internal tide. That tide is squeezed through a throated nozzle, accelerating into a massive hydraulic slug of water. That slug slams upward into a rigidly reinforced titanium chamber, compressing an already dense 80-bar pocket of air into a hypercharged gas spring.
Yep.
And then that pressurized air bursts through a check valve into a high-pressure buffer tank where it is smoothed out into a perfect steady stream. We have captured the wave, intensified the pressure, and smoothed the flow.
We have engineered the perfect pneumatic environment. The energy is ready to be extracted.
Right. But now we have to face the terrifying reality of deep ocean maintenance. Where do we actually put the incredibly delicate, rapidly spinning turbine? Because if we put a complex piece of turbo machinery full of sensors and bearings in a wet, highly corrosive 80-bar environment, isn't it just going to get instantly destroyed? Or cost $1 billion to fix every time a bearing squeaks?
That is the exact trap that has killed dozens of deep ocean energy concepts in the past. If you put your most sensitive, maintenance-heavy components at 800 meters, your operational expenditures will bankrupt the project.
It's just not viable.
But Enfield sidesteps this trap entirely with subsystems 4 and 5, the climb to the surface.
If you're listening to this and trying to picture the plumbing, you're probably thinking, wait, we have an 800-meter-long pipe just acting as an exhaust. But here's where it gets really interesting. We don't put the turbine at 800 meters at all.
Subsystem 4 introduces the dry turbine shaft. We have to remember what the first 3 subsystems accomplished. We transferred the raw kinetic energy of the ocean water into a closed, isolated, gas-phase pneumatic circuit.
The power is no longer in the water. The power is in the air.
Exactly. And pumping dry, pressurized air upward through a pipe is infinitely easier than building an 80-bar waterproof deep-sea turbine housing. The architecture routes the smooth flow from the high-pressure buffer tank up a completely dry vertical shaft. The actual turbine, the generator, the delicate electronics, they are placed much closer to the surface. The paper suggests a nominal depth of 50 to 150 meters.
I love the elegance of this architectural trick. It's exactly how you design a submarine. You don't bolt the delicate radar electronics to the outside of the pressure hull where the water can crush them, right?
Right, you keep them safe.
You build a conning tower to house the sensitive equipment. In this case, we keep the heavy, brute force hydraulic piston work down in the crushing depths where the internal tides live. But we pipe the clean, pressurized air up to a conning tower at 50 meters, where we place the actual engine of the machine.
It fundamentally changes the economics of the machine. At 50 to 150 meters, we are no longer in the exotic sci-fi realm of abyssal engineering. We are firmly in the realm of standard, commercial, offshore oil and gas engineering.
Which is huge for costs.
The sealing technologies, the access hatches, the maintenance protocols, these are all solved problems. A standard commercial dive team or a basic support vessel can access a turbine at 50 meters. You don't need a multi-million-dollar experimental robotic submersible just to swap out a faulty temperature sensor.
And the vertical shaft itself plays a role in the fluid dynamics, right?
Mm.
It's not just an empty elevator shaft for the air.
No, the geometry of the upper shaft is highly specialized. The paper details the inclusion of a nozzle section immediately upstream of the turbine rotor. As the pressurized air climbs the shaft, it enters this narrowing throat. Once again applying the continuity relationship, the air is forced to accelerate dramatically right before it strikes the turbine blades, maximizing the kinetic energy transfer.
But the paper warns against making that nozzle too narrow, right? You can't just squeeze it down to a pinhole to get a jet stream.
If you aggressively narrow the throat too much, you introduce massive frictional and viscous losses. Worse, you risk choking the flow entirely.
Choking it.
If the air hits a bottleneck and backs up, the pressure wave travels all the way back down the 800-meter pipe, enters the buffer tanks, and ruins the carefully tuned compliance of the mass spring system at the bottom. The entire machine would stutter and stall. It is a very delicate aerodynamic balance.
Wow. So the air rockets through the nozzle, spins the turbine at 50 meters depth, and generates the electricity. But that dry shaft doesn't end at the turbine. It continues upward, eventually breaking through the surface of the ocean into the open air. Which brings us to Subsystem 5, the Wind Assist Vortex Cap.
This is perhaps the most clever finishing touch to the entire pneumatic circuit. The cap sitting on top of the structure above the waves isn't just an exhaust grate to vent the spent low-pressure air into the sky. It is a highly engineered aerodynamic flow organizer.
The sources reference guidelines from the Department of Energy and NIST regarding stack effect analysis. What exactly is the stack effect in this context?
The stack effect is a natural phenomenon driven by differences in density and temperature between the air inside a vertical shaft and the air outside. Generally, warm, lighter air naturally wants to rise up a chimney.
Okay, like a fireplace.
Right. By designing the thermal properties of the 800-meter shaft correctly, Enfield creates a natural, persistent upward draft that constantly pulls air from the bottom to the top. But the cap at the surface takes this a step further. It is aerodynamically shaped to interact with the ambient coastal winds blowing across the open ocean.
Oh, I see. It's like blowing across the top of a glass soda bottle.
Yes.
As the high-speed surface wind blows across the uniquely shaped vortex cap, it creates a zone of low pressure directly over the opening of the shaft. That low-pressure zone literally sucks the exhaust air up and out of the machine.
Exactly. It uses the Bernoulli principle to add a constant free suction force to the top of the pneumatic circuit. The paper calculates that this wind-driven draft could contribute a 5 to 10% airflow augmentation under favorable weather conditions.
5 to 10% might sound like a rounding error to a casual listener, but when you're trying to squeeze commercial margins out of a massive capital infrastructure project, a free 10% boost in efficiency is the difference between an idea dying on a whiteboard and actually getting funded.
It is the absolute margin of commercial viability. And it justifies the paper's claim that the SPH-BOWC is not just a wave energy device, it is a true hybrid machine.
A hybrid.
It is a wind-wave pressure hybrid. The wet chamber at the bottom harvests the internal tide. The 80-bar hydrostatic pressure densifies the pneumatic gas spring. The buffer loop smooths the delivery. And the wind-assisted vortex cap mechanically pulls the exhaust through the turbine. Every single environmental factor is harnessed.
It is an incredibly elegant, interconnected structural symphony. But if I put my skeptic's hat on listening to this, 800-meter deep titanium chambers, 80-bar dynamic gas springs, perfectly tuned acoustic buffer loops, 150-meter dry shafts breaking the surface. It all sounds like a massive, impossibly complex sci-fi megastructure.
It certainly does.
If I'm an investor looking at this pitch deck, I'm thinking this is brilliant, but it is going to take 50 years and $1 trillion in pure R&D just to invent the materials to build this thing.
And that skepticism is entirely warranted. Sinking a dynamically oscillating machine into the abyssal zone is historically a fool's errand. But Section 5 of Enfield's paper directly counters that skepticism.
Okay.
He argues that we actually don't need to invent this technology from scratch. We simply need to borrow it.
Section 5. Borrowing from neighbors. This is where the paper stops being theoretical and looks at the adjacent real-world technologies that are maturing right now, making this machine possible today. Let's start with UWCAES, underwater compressed air energy storage. We mentioned it briefly with the buffer tanks, but how massive is this industry right now?
It is rapidly becoming one of the most vital fields in renewable grid management, and it is the closest commercial analog to what Enfield is proposing. The paper highlights several active projects, most notably a company called Barramar, which is partnering with the global engineering firm Jacobs.
And what are they doing?
They are currently developing a massive pilot project off the coast of Cyprus.
What exactly is Barramar building at the bottom of the ocean?
They are building enormous, rigid tanks made of concrete and steel. They ballast these tanks to the seafloor. When the local power grid has excess energy, say, the sun is shining brightly on solar panels but nobody is running their air conditioners, they use that cheap electricity to run giant compressors.
Okay.
They pump compressed air all the way down into those subsea tanks, displacing the water inside them.
So they are inflating a giant balloon underwater.
Exactly. And when the sun goes down and the grid suddenly needs power, they open a valve. The immense, crushing hydrostatic pressure of the ocean automatically squeezes the tank, forcing the highly compressed air back up the pipe to spin a turbine on the surface. They are targeting an astonishing round-trip efficiency of 70 to 85%.
The sources note that 80% efficiency is comparable to pumped hydro storage, which is currently the absolute gold standard for grid-scale energy storage. And what are the economics of the Barramar system?
Project developers are estimating capital costs in the range of $1,500 to $2,500 per installed kilowatt. In the world of massive grid storage, that is highly competitive.
The sources also mention a variant of this called IDOCs, isothermal deep ocean CAs.
This is a crucial evolution of the technology that directly benefits our wave machine. When you heavily compress air, as we discussed earlier, it generates a massive amount of heat. In traditional land-based compressed air storage facilities, that heat bleeds off into the atmosphere and is lost. When you lose that heat, you lose efficiency.
Right.
But in the deep ocean, the environment solves the problem. The surrounding abyssal water is near freezing. It acts as an infinite thermal sink. It rapidly absorbs and manages the heat of compression, maintaining near isothermal conditions inside the tanks.
It uses the freezing ocean to water cool the battery.
Precisely. And research suggests that leveraging this deep ocean thermal mass could drive energy storage costs down to an astonishing $1 to $10 per kilowatt hour stored.
That is absurdly cheap. But how does Barramar building a giant battery in Cyprus help Enfield build a wave energy catcher?
Because the SPHB-OWC's central chamber and high-pressure buffer tanks rely on the exact same thermodynamic principles, they will benefit from that identical deep ocean thermal regulation. But more importantly, the UWCAES industry is doing the expensive, painful trial and error R&D right now.
Oh, they're paving the way.
Yes. They are figuring out how to build flexible isobaric accumulators. They are solving the sealing issues of underwater gas-water interfaces. They are de-risking the exact subcomponents Enfield needs.
It's an exercise in convergent engineering. Enfield doesn't have to raise $1 billion to figure out how to keep a subsea valve from freezing at 80 bar. Barramar and companies like Brayton Energy are already spending that money. In 5 years, Enfield can just buy the validated valves off the shelf.
He is drafting in the wake of a heavily funded adjacent industry.
And it's not just the mechanical valves, it's the physical materials required to build the hull. The paper details a deep-sea materials revolution that is happening right now, completely independent of wave energy. Let's look at the materials Enfield wants to use, because they sound like they belong on a Mars rover. First on the list, geopolymers.
Geopolymer composites are rapidly emerging as the premier structural material for extreme depth. We are talking about operating beyond 1,000 meters deep. Traditional concrete struggles at these depths because microscopic voids allow water to intrude.
And what happens then?
Over time, the extreme pressure crushes the material from the inside out.
The water acts like a wedge, splitting the concrete apart.
Yes. But geopolymers rely on entirely different chemical bonding. They form a dense, inorganic polymeric network that boasts ultra-low permeability. Water simply cannot penetrate the microstructure. The sources report that these next-generation geopolymers can achieve compressive strengths up to 100 megapascals. They are completely immune to the crushing forces at 400 bar, and they are moving out of the lab and into field demonstrations for deep-sea mining equipment right now.
Then there is the metal for the chamber itself. The paper specifies 5 series aluminum, specifically an alloy called 5806. And when I read this section, my brain short-circuited.
Well, it is quite surprising.
The paper points out a totally counterintuitive fact. This specific aluminum alloy actually resists corrosion better when you drop it 2,000 meters deep than it does when it's sitting 10 meters below the surface. How is that chemically possible? Salt water is salt water, isn't it?
It is not the salt that destroys the metal, it is the oxygen. When you put metal and salt water near the surface, there is a high concentration of dissolved oxygen mixed into the water from the atmosphere and from photosynthesis. That oxygen acts as a catalyst, aggressively fueling the electrochemical oxidation process that causes rust and corrosion.
Right, the oxygen eats the metal.
But as you descend into the abyssal zone, the dissolved oxygen profile of the ocean drops precipitously. The deep water is ancient. It hasn't interacted with the atmosphere in centuries. Without that high concentration of oxygen to fuel the reaction, the oxidation chemistry fundamentally stalls.
That's amazing.
Certain alloys, like 5A06, form a stable passivation layer and essentially stop corroding. The hostile deep ocean actually protects the metal, drastically extending its operational lifespan compared to a surface machine.
That is just incredible. The very environment we thought was destroying our machines is actually preserving them. And finally, the paper leans into additive manufacturing, 3D printing for the abyss.
Specifically, the 3D printing of titanium shells. Titanium is the absolute premium choice for deep-sea pressure vessels because of its unparalleled mass-to-strength ratio and complete immunity to seawater corrosion.
So why don't we use it for everything underwater?
The problem has always been fabrication. Forging and machining massive, geometrically complex titanium chambers is prohibitively expensive and wastes huge amounts of material.
But if you 3D print it,
Additive manufacturing changes the economic equation entirely. You deposit the titanium powder exactly where it is needed, layer by layer, building complex internal lattices and curves that would be impossible to machine from a solid block. The latest research confirms that thin-walled, 3D-printed titanium structures can achieve the exact same compressive strengths as solid forged vessels, but at a fraction of the weight and fabrication cost.
Okay, so let's summarize the reality check here. The physics of the 80-bar gas spring are mathematically sound and validated by thermodynamics. The mechanical subsystems, the buffer loops and valves, are currently being built and de-risked by the multi-million-dollar UWCAES energy storage industry. And the futuristic materials, the geopolymers and the 3D printed titanium, are successfully exiting the laboratory phase.
Everything seems to be lining up.
Right, so if all of these puzzle pieces genuinely exist in the real world, why aren't we chartering a boat and dropping one of these into the ocean tomorrow? What is the catch?
The catch is that combining all of these disparate pieces into a single, highly tuned, dynamically oscillating machine at 800 meters is an exponentially complex, terrifying engineering task.
It's not a walk in the park.
Not at all. The paper includes a systematic risk registry, and to Enfield's credit, it is brutally honest about the failure modes.
Let's walk through the ways this thing could catastrophically fail. Because to be truly well-informed, we can't just look at the rosy projections and the clever math. We need to look at the bottlenecks. The first failure mode is labeled a high risk, gas spring management.
We discussed the paired penalty of the incredibly stiff gas spring at 80 bar. The risk is that the mathematical tuning required to make that spring yield to the water piston is hyperspecific to the exact depth of the installation.
Okay, meaning?
If you engineer the compliance accumulators, the chamber volumes, and the throttle valves perfectly to capture a 3-meter internal tide at precisely 800 meters depth.
And you try to take that exact same machine, roll it off the boat, and deploy it at 600 meters or 1,000 meters instead.
It fails immediately.
Immediately.
Yes. At 600 meters, the ambient pressure is only 60 bar. The carefully tuned 80 bar spring is now too soft. The water piston will surge upward with too much velocity, physically slamming into the top of the chamber and destroying the internals.
Oh, wow.
And at 1,000 meters, the pressure is 100 bar. The spring is far too stiff, and the water piston won't be able to compress it at all. The system locks up.
So you cannot build a massive factory that just churns out one-size-fits-all SPHBOWCs. Every single machine has to be a bespoke, custom-engineered piece of hardware tuned perfectly to the specific bathymetry of its deployment site.
Exactly. It requires highly specific iterative computational fluid dynamics modeling for every single unit. That is a massive bottleneck for commercial scaling.
Okay, that's a huge hurdle. The second high risk on the registry is structural integrity. And here's where I want to push back a little bit on the paper's pessimism. We build deep-sea oil pipes, manifolds, and wellheads all the time. They sit at 2,000 meters deep for decades without imploding. What is the fundamental difference between an oil pipe surviving at depth and this high-bar chamber surviving?
The crucial difference is static pressure versus cyclic fatigue. An oil pipeline sits on the seafloor under a constant, unchanging hydrostatic load. The pressure pushes inward with 200 bar of force, and the steel pushes back with 200 bar of force, and they reach a stable equilibrium.
It is a static vessel.
Exactly. The SPHBOWC chamber is experiencing that exact same massive external pressure, but it is simultaneously being punched from the inside by a massive hydraulic water piston millions of times a year.
Because the internal wave is constantly rising and falling, drastically spiking the pressure inside the chamber over and over again.
Yes. Think of it like this. Imagine you are an athlete holding a massive 200-pound iron weight above your head. That is the hydrostatic pressure.
Okay.
If you are strong enough, you can lock your elbows and hold it there indefinitely. But now imagine that while you are holding that massive weight above your head, someone is repeatedly punching you in the stomach. That is the dynamic cyclic wave loading.
It's the combination of the two forces that causes you to collapse.
Fatigue under combined hydrostatic and dynamic loading is the single primary structural failure mode in deepwater infrastructure. It is incredibly difficult to model and predict. To make matters worse, deep-sea rock mechanics research shows that extreme confining pressure actually changes the physical nature of materials, causing what is known as a brittle to ductile transition.
Meaning the metals bend and snap differently at 800 meters than they do in a lab on the surface.
Exactly. A titanium alloy that might safely flex and rebound 1,000,000 times at 10 liters depth might snap like brittle glass at 800 meters when subjected to cyclic loading, because the extreme confining pressure prevents the crystal lattice of the metal from slipping naturally.
That's wild.
Standard surface engineering predictions break down. To survive a 20-year operational lifespan, the chamber must be over-engineered with massive, expensive safety factors.
That is genuinely terrifying from an engineering perspective. Okay, what about the medium-high risk? Sealing.
Maintaining a waterproof seal against 80 bar of pressure is a known challenge. But the SPHBOWC requires maintaining a perfect seal across a continuously moving gas-water interface. The water piston is rising and falling violently at cycling rates of 0.05 to 0.2 hertz.
So that's a new wave punching the machine every 5 to 20 seconds, continuously, without a break, for 20 years.
Yes. The UWCAES energy storage systems we talked about earlier use highly engineered flexible membranes or bladders to separate the compressed air from the seawater, but a grid storage battery might cycle once a day, slowly charging at night and slowly discharging in the afternoon.
Our machine demands millions of violent, rapid cycles.
The fatigue life of flexible membranes, bellows, or sliding mechanical seals at high-bar cycling rates is, frankly, an unsolved engineering question. If that seal degrades and 80-bar seawater violently breaches the pneumatic circuit, the machine is instantly destroyed.
And if it does break, we hit the medium risk, maintenance. Even if we took your clever submarine analogy and placed the delicate turbine at a manageable 50 meters, the giant titanium chamber, the complex compliance valves, and the intake funnels are still sitting in the dark at 800 meters.
And human divers, no matter how advanced their atmospheric suits are, cannot perform heavy construction at 800 meters. Any maintenance, any inspection, any replacement of a jammed throttle valve requires a heavy-duty remotely operated vehicle, an ROV, or a specialized work-class submersible.
You can't just send a guy out in a Zodiac inflatable boat with a wrench, which is how they fix surface OWCs.
Definitely not.
You need a 300-foot dedicated offshore support ship holding station above the site, deploying a $1 million robot just to look at the machine. That operational expenditure, the OPEX, could eat up every dime of electricity profit the machine generates.
And finally, the last major hurdle, site specificity. You cannot just drop this machine anywhere in the ocean and expect it to work.
Why not?
Because the entire architecture relies on internal tides interacting with specific bathymetry to create shoaling effects and resonance, you need highly specific, perfectly shaped underwater mountain ranges,
Oh, right.
Finding those sites requires incredibly expensive, high-resolution, deep ocean sonar surveys and years of acoustic Doppler current profiling. You can't just look at a satellite map of surface winds. You have to hunt for the invisible energy.
Okay, so knowing all of this, the terrifying reality of cyclic fatigue, the risk of brittle titanium snapping, the unsolved problem of high-speed 80-bar seals, and the astronomical costs of ROV maintenance, and knowing that wave energy in general is currently incredibly expensive. How does Enfield propose we actually get this thing built? Who is going to write the check for this?
We have to look at the macroeconomics of the energy sector and the overarching trajectory of marine energy research. Section 7 of the paper is where Enfield lays out the harsh economic reality, contextualized by the levelized cost of energy, or LCOE.
Let's talk actual numbers. The sources state that the current LCOE for pilot-scale wave energy devices sits somewhere between €0.37 and $1.22 per kilowatt hour.
Which is wildly, almost comically uncompetitive. Modern offshore wind turbines are generating power for a fraction of that cost.
Right.
However, the Department of Energy's National Renewable Energy Laboratory, NREL, and the European Strategic Energy Technology Plan have established very clear, aggressive targets for the industry. To become a relevant part of the global grid, marine energy needs to get down to the $0.30 per kilowatt hour range by 2030, and ideally drop below $0.15 per kilowatt hour in the long term.
How on earth do we get from $0.22 down to $0.15? The paper says we obviously need massive reductions in capital expenditures, but it also highlights a shift in engineering philosophy called broadband capture.
That's a very important concept.
I want to bring up the 2026 University of Osaka research that the sources mentioned, because I think it explains this perfectly. They were studying highly complex gyroscopic wave energy converters.
Yes, the Osaka research highlights the critical, fundamental shift in how the field thinks about the ocean. For decades, wave energy devices were designed around the principle of resonance. Engineers would design a machine tuned perfectly to capture maximum energy from one specific size, height, and frequency of wave.
They tune the machine to catch the average wave.
Right.
But the ocean doesn't give you the exact same average wave over and over again. The ocean is chaotic. It gives you a 10-foot crashing wave, then a 2-foot roller, then a messy cross-chop.
Exactly. If the waves were too small, the resonant machine didn't move. If the waves were too big or too fast, the machine was thrown entirely out of phase and captured almost nothing. It was a very narrow band of capture.
Which means lots of wasted energy.
Exactly. The future of marine energy is broadband capture. Engineers are realizing they must build systems that can efficiently harvest whatever chaotic, messy energy the sea is throwing at them across a very wide frequency spectrum.
The Osaka gyroscopic research mathematically proved that if the mechanical architecture is adaptable enough, you can theoretically capture up to half of the total incident wave energy across a broad spectrum of wave states.
And Enfield forcefully argues that the SPHBOWC is architecturally designed from the ground up for broadband capture.
How so?
The stepped bathymetric intakes can couple to different forcing frequencies as the internal tide shifts. The complex compliance volumes and side accumulators allow the incredibly stiff 80-bar gas spring to dynamically detune itself on the fly to match whatever water piston speed is occurring.
Oh, that makes sense.
And crucially, the closed-circuit buffer tanks completely isolate the delicate turbine from the chaotic, instantaneous wave state.
The machine essentially eats the wild, broadband messiness of the ocean, digests it in the buffer tanks, and spits out a clean, uniform breeze for the turbine.
It is entirely aligned with the dominant, near-future research direction of the entire marine energy sector. It abandons narrow resonance for broad adaptability.
So we have a machine that fits the economic theory. How do we actually build it without going bankrupt on the first try? The paper proposes an incredibly patient, disciplined, 4-phase roadmap.
Yes, Enfield is very pragmatic here.
Ah.
Phase 0, covering years 1 and 2, involves absolutely zero construction. No metal gets bent. No concrete gets poured.
Just numbers.
It is purely computational. It requires immense supercomputing time dedicated to CFD modeling of the intakes, thermodynamic simulation of the adiabatic gas springs, and rigorous finite element analysis of the cyclic structural fatigue on the titanium. You have to prove the math works across a massive parameter space before you ever touch the water.
Then we move to phase 1, spanning years 2 to 5. We finally build a physical prototype, but we do not drop it to 800 meters. We install it at a nominal depth of 50 to 150 meters. I think this is the smartest part of the whole roadmap. Why do we start in the shallow end?
Because at 50 to 150 meters, you are still subjecting the machine to meaningful elevated hydrostatic pressure around 5 to 15 bar. 5 to 15 bar That is enough pressure to experimentally validate the stiffer gas spring physics, test the compliance accumulators, and verify the flow through the pneumatic buffer loops.
But crucially, at 50 meters, you don't have to hunt for mysterious internal tides. You can still use easily measurable, highly visible surface waves to drive the water piston.
Exactly.
You aren't fighting the dark, unknown abyssal environment yet. You're just validating the core pneumatic physics in a highly manageable, easily accessible environment.
Then comes phase 2, covering years 5 to 10, which is the crucible. This is the true deep prototype deployed at 400 to 800 meters. And notice the stated goal for this phase. The focus is absolutely not on generating commercial grid power or hitting LCOE targets.
Right, the goal is just, can this thing stay alive?
The sole focus is survivability. Can the device survive completely unmaintained, relying solely on invisible internal tides for 6 to 12 months without the flexible seals rupturing, the throttle valves jamming, or the titanium hull cracking under cyclic fatigue? It is purely a physics and structural validation mission.
And finally, phase 3, stretching into years 10 and beyond. This is the grid-connected commercial pilot. This is where you connect the 50-meter turbine to a subsea export cable, send the power back to the shore, and actually figure out the real-world LCOE to see if you can hit that aggressive $1.15 target.
If we connect this to the bigger picture, this staged roadmap proves that Enfield deeply understands the reality of his own terrifying proposal. He isn't acting like a tech bro promising a magic bullet that will solve global energy next year.
No, not at all.
He explicitly states that operating at 800 meters fundamentally changes the class of the machine. It requires a serious, patient, highly disciplined, decade-long development program. It does not make it impossible. It makes it serious.
I absolutely love that quote from the conclusion of the paper.
It is a sobering but necessary acknowledgement of the engineering reality.
So what does this all mean? We've covered a tremendous amount of deep, complex ground today.
If we synthesize the journey we've just taken, the SPHBOWC takes established, almost boringly reliable physical principles, the thermodynamics of rapid gas compression, the mass flow continuity equation, standard hydraulic pistons, and natural stack effect drafts.
And it combines them in an entirely novel, deeply counterintuitive architectural framework.
Right. It takes the ocean's terrifying, crushing pressure, the exact force that destroys submarines, crushes steel drums, and makes deep-sea engineering a living nightmare. And it says, no, this is no longer our enemy. This is our greatest asset.
This is our massive free amplifier.
It completely flips the script. It treats the hostile environment as an ally. And by taking that leap of faith, it opens up a viable theoretical pathway to harness the massive, largely untapped kinetic energy of deep internal tides.
It uses the very seabed itself as a structural funnel. It shapes the chaos of the ocean into a controlled strike. And it isolates the delicate machinery in a protective buffer, turning the violent abyss into a predictable, smooth power source.
It's an incredible piece of structural logic.
For you listening today, this is exactly the kind of structural deep dive we are always hunting for. It takes a topic that initially seems impossibly dense, deep ocean thermodynamic physics and cyclic material fatigue, and reveals the incredibly elegant structural logic underneath it all.
It's entirely about shifting perspective.
Yeah, it's about staring at a massive, insurmountable barrier and realizing it's actually the exact tool you need to succeed.
And that profound shift in perspective leads to a fascinating broader implication. This paper raises an important question that extends far beyond just marine energy.
Oh, like what?
If the SPHBOWC fundamentally flips the script by using extreme hydrostatic pressure as a foundational required tool rather than a barrier to be fought, what other extreme natural forces are we currently ignoring?
Oh, wow. I like where this is going.
Think about the billions of dollars that engineering world spends right now to fight extreme environments. We spend fortunes trying to cool down and insulate drill bits from the extreme volcanic heat in deep geothermal drilling.
Yeah.
We spend millions engineering complex aircraft engines to fight the brutally low atmospheric pressure and thin air at high altitudes. We build massive, heated structures to insulate against the extreme cold of the Arctic. We view all of these environmental extremes as pure penalties.
Hey, the enemy. We just want to keep them out.
But what if we applied Enfield's architectural philosophy to those fields? What if we stopped playing defense? What if we stopped trying to keep the extreme environment out and instead completely redesigned our thermodynamic cycles and machines to require that extreme environment to function at all?
Designing a machine that only works, that only generates power because it is encased in 500-degree volcanic rock, or because the ambient air is impossibly thin, or because it is freezing cold. That is a massive paradigm shift. It brings us right back to our opening thought, dropping the steel drum into the ocean. We need to stop building thicker walls and start inviting the extreme physics inside. That is an incredibly powerful, lingering thought to chew on.
It really is.
Thank you to you, our listener, for sending in such complex, thought-provoking, and deeply structural source material for today's deep dive. Until next time, keep looking for those aha moments.
You know, when we think about harnessing the ocean's power, our minds usually go to these massive waves crashing on the surface, right? But what if the real power isn't in the splash and the crash, but in the immense silent pressure of the deep ocean itself? Well, today we're going to explore a radical new concept that does exactly that. This quote from the concept's author, Zachary David Enfield, just perfectly sets the stage. It forces you to reframe the deep sea. It's not some hostile barrier we have to overcome, but a unique and incredibly powerful resource that's just waiting to be tapped into. And that really leads us to the central question here. What if we could actually take that constant, crushing pressure you find 800 meters below the surface and use it as a massive advantage for generating energy? Okay, first things first, let's get into the core physics that could make this a total game changer. It's all about using depth not just as a place, but as a design variable, one that literally multiplies the force you can get from the water. So let's look at a direct comparison. On the left, you've got your standard oscillating water column, or OWC. It's a pretty common device where surface waves push water up, compress some air, and turn a turbine. But now look at the right. This is the high bar concept. At 800 meters down, the baseline pressure is already 80 times higher. So when a deep ocean current pushes the exact same amount of water into the chamber, the pressure swing it creates is 80 times larger. And that's the number to remember. 80 times the pneumatic, the air pressure, force. It's the same movement of water, but it yields a vastly more powerful result, simply by changing the operating environment from the surface to the deep sea. Now, it's really important to get this straight. This isn't some kind of free energy machine that's creating power from static pressure. No, the machine uses that immense baseline pressure as an amplifier. It makes every single push of water, every pulse, an incredibly dense and powerful event that you can then convert into electricity. So how would a machine like this actually work way down there in the dark? Well, the whole design is based on 5 interconnected subsystems, and each one is a really clever solution to the unique challenges of operating so deep. First up, how do you capture energy if you don't have any surface waves? The answer is something called the abyssal pulse piston. The intake isn't just some passive hole. It's specially shaped to capture energy from deep currents, and even from these things called internal waves. They're like waves between different layers of water. It organizes all that flow into a powerful, coherent slug of water that acts just like a piston. So that piston creates these wild, chaotic pulses of pressure, which, as you can imagine, isn't very efficient for a turbine. The solution is a pneumatic buffer loop. The best way to think about it is like an AC to DC converter for your electronics. You've got check valves and buffer tanks that take all those chaotic pulses and they smooth them out into a steady, high-pressure flow that the turbine can use super efficiently. Now, this might be one of the smartest parts of the whole design, where they put the turbine. It's not at 800 meters. See, because the energy has been converted into a flow of compressed gas, the turbine itself can sit in a dry shaft, much, much closer to the surface. This is huge. It protects it from that super corrosive, high-pressure environment and makes maintenance way, way easier. And here's another clever little touch, the surface cap. The shaft that houses the turbine ends at the surface with this specially shaped cap. It basically uses the ambient wind, kind of like a chimney, to help pull the exhaust gas out. This could boost airflow by a very helpful 5 to 10%. It's a true hybrid machine. Okay, so this all sounds amazing, but this concept is at the very, very beginning of its journey. To really understand its potential, we have to ground it in the reality of today's engineering and, of course, the economic challenges. The biggest hurdle for all wave energy is cost. I mean, just look at these numbers. Current wave energy is way more expensive per kilowatt hour than established renewables like offshore wind. The entire industry, and that includes this new concept, has to find a way to close this major cost gap if it's ever going to be commercially viable. So where does this stepped pressure concept, the SP-HBWC, fit in? Well, you can see it's right at the bottom, at technology readiness level 1 to 2. That means it's basically a formalized concept on paper right now. But the good news is, it doesn't have to start from scratch. It can build on lessons learned from more mature technologies, like commercial OWCs and underwater energy storage systems. And yeah, the engineering risks, they are substantial. I mean, managing the incredibly stiff gas spring that gets created at 80 bar pressure is the top challenge. The structure also has to survive that immense pressure for over 20 years. The seals have to work perfectly for millions of cycles. Oh, and the whole thing has to be installed and maintained with robots. These are serious problems for sure, but they're not impossible. So, given those challenges, what's the path forward? You don't just jump into building something this ambitious. The concept paper actually lays out a very deliberate multi-year plan to prove the technology step by step. The roadmap is really methodical. It starts with 2 years of just computer modeling, no metal gets cut, then a 5-year phase building a prototype at a more manageable depth to make sure the physics works, and only after all that would they build a true deep water prototype, eventually leading to a grid-connected pilot in maybe 10 years or more. This is a long-term, serious research effort. You know, the timing for an idea like this might actually be perfect. It doesn't have to invent everything from the ground up. It can leverage all these advancements happening in other fields: better underwater storage, stronger deep-sea materials, more advanced controls. It's really aligned with where the whole marine energy sector is already heading. Which brings us right back to this final thought. Taking this technology 800 meters deep doesn't make it impossible. It makes it a serious piece of engineering. It elevates the potential from some niche device to a machine that could fundamentally change how we think about ocean power. And really, the question it leaves us with is, what other immense, untapped resources are just waiting for us if we only change our perspective?